Hello, welcome to my video series of algorithms. This is part 8 of Module 2, Logic and Proof. In this video, we will discuss math induction. Math induction is often used to prove propositions whose domains are sequences. A sequence, in general, is a list of ordered elements. Formally speaking, a sequence is a mapping from a subset of non-negative integers 0, 1, 2, all the way through n, to a set S. The non-negative integers are called indexes, and the elements in the set S are called terms. Let's consider a sequence that contains the elements A0, A1, A2, all the way through AN. The subscripts 0, 1, 2, all the way through n are the indexes. And A0, A1, A2, all the way through AN are the terms, which compose the set S. The indexes indicate the order of the elements. Among the terms, A0 is called the initial term. Every sequence must have an initial term. The term AN is called the final term. A sequence may or may not have the final term. If a sequence has the final term, it is called a finite sequence. Otherwise, it is called an infinite sequence. A mapping function exists that maps an index k to a term ak. For example, the student names ordered by their IDs are a finite sequence. The indexes are the student IDs. The terms are the student names. The mapping function maps a student ID to a student name. In many cases, the domains of propositions can be sequences. For example, consider the proposition: for every non-negative integer x, there exists a prime number that is larger than x squared. The domain of this proposition is the set of squares of non-negative integers, that is, 0, 1, 4, 9, and so on. In this case, we can view the non-negative integers x as the indexes. Their squares are the terms. The mapping function that maps the indexes to the terms is fx equals x squared. The initial term of the sequence is a0 equals 0. There is no final term of the sequence. Therefore, it is an infinite sequence. Math induction is a technique to prove propositions whose domains are sequences. The key idea of math induction is to leverage the dependency among the terms of the sequence. That is, knowing the proposition is true of some terms makes proving the proposition on some other terms easier. Specifically, it tries to prove PAK plus 1, which means the proposition evaluated at the term AK plus 1 is true, using the premises that PA0 through PAK are true. Know that k plus 1 is an arbitrary index. Therefore, we can claim that the proposition P is true on the entire sequence, or the entire domain. In many cases, directly proving PAK plus 1 for arbitrary index k plus 1 is difficult. With math induction, we will have access to additional conditions, PA0 through PAK, which could make proving PAK plus 1 much easier. We will see the logic behind the technique and derive its key procedures. The major effort of math induction is to prove PAK plus 1 is true when PA0 all the way through PAK are true, where k is larger than or equal to 0. We will begin by investigating the logic with a special case. Say we are trying to prove PAK plus 1 when PAK is true, where k is larger than or equal to 0. That is, we do not require the proposition P to be true for all terms preceding AK plus 1, just that PAK is true. Let's see what can we get if we can prove PAK plus 1 using PAK. Since k is an arbitrary index, we can unfold it by assigning specific indexes. That is, if we can prove for arbitrary index k plus 1, PAK plus 1 is true if PAK is true, we know that PA1 is true if PA0 is true. In addition, PA2 is true if PA1 is true, and so on. We depict the dependency as the figure in this slide. You can see that proving the proposition on the current term depends on proving the proposition on the previous term. However, at this point, we still can't say the proposition is true on all terms. Because although we have shown that PAK plus 1 is true when PAK is true, we have not shown that the condition PAK is true. Therefore, we cannot assert that the conclusion PAK plus 1 is true. Do we need to show all conditions are true? No. It turns out that we only need to show that the proposition is true with the initial term. That is, we only need to show PA0 is true. The process of showing PA0 is true is called the base step of math induction. Usually, the base step is easy, as A0 is a concrete element with a specific value. We can easily plug it into the proposition and verify its truth value. Now, say we have shown PA0 is true and marked the very first circle in the figure green. Let's see what can we get. Again, suppose that we have shown that PAK plus 1 is true if PAK is true. We know PA1 is true if PA0 is true. In the base case, we have shown that PA0 is true. Together, we know PA1 is true. From the previous reasoning, we know PA1 is true. We also know that PA2 is true when PA1 is true. Together, we know PA2 is true. Using the same logic, we will be able to show that the proposition is true on all terms of the sequence. Note that the same logic and conclusion apply to both finite and infinite sequences. Let's review what have we done and summarize the procedure of math induction. Recall that the crux of math induction is to prove PAK plus 1 is true when PAK is true. First, we begin with the base step and show that PA0 is true. Then, we will assume that PAK is true for all k that is larger than or equal to 0. This step is called the induction hypothesis. Know that when we make the hypothesis, the range of the index k is very important. The range of k must cover the base case. That is, k should be able to take the value 0. Otherwise, we won't be able to get that PA1 is true from PA0, and the chain of reasoning will be broken. Once we have assumed that PAK is true for all k is larger than or equal to 0, we will then show how it can lead to that PAK plus 1 is true. This process is called the induction step, which is the core part of math induction. Note that in some cases, they would assume PAN and prove PAN plus 1, or assume PAK minus 1 and prove PAK, and so on. The differences in the indexes do not matter, as long as the induction hypothesis covers the base case. At last, we will need to conclude what we have done and claim that the original statement is correct. Let's look at a real example. Prove that for every positive integer k, 11 to the power of k minus 6 is divisible by 5. The domain of the proposition is positive integers. Therefore, the initial term is 1, the smallest positive integer. In the base step, we need to show that the proposition is true when k equals 1. This is easy, as 11 to the power of 1 minus 6 is 5, which is divisible by 5. And we have completed the base step. Then, we will make the induction hypothesis. We assume that for any positive integer k larger than or equal to 1, 11 to the power of k minus 6 is divisible by 5. Note that the smallest value k can take is 1, which covers the base case we just proved. Then, we need to show that 11 to the power of k plus 1 minus 6 is also divisible by 5 in the induction step. Simplifying 11 to the power of k plus 1 minus 6, we get 11 times 11 to the power of k minus 6 plus 6 minus 6. Since 11 to the power of k minus 6 is divisible by 5, we will denote 11 to the power of k minus 6 as 5x, where x is an integer. Substituting 11 to the power of k minus 6 with 5x, we get 11 to the power of k plus 1 minus 6 equals 5 times 11x plus 12. Since x is an integer, 5 times 11x plus 12 is divisible by 5. Therefore, 11 to the power of k plus 1 minus 6 is also divisible by 5. At last, we conclude that the original statement is correct. The conclusion step is usually included for the completeness and formality of the proof. Recall that in the above math induction logic, the core statement we need to prove is that PAK plus 1 is true when PAK is true. It is a special case of the general version. PAK plus 1 is true when PA0 through PAK are all true. The special case requires fewer premises, hence it makes a weaker assumption about the proposition. In this case, we call this type of induction weak induction. In weak induction, proving PAK plus 1 is true only depends on the premise that PAK is true. In the more generalized case, we will need the premises of PA0 through PAK to be all true to prove PAK plus 1 is true. That is, showing the proposition is true on the term AK plus 1 requires that the proposition is true on all terms preceding AK plus 1. The dependency relation is shown in the figure. This type of induction is called strong induction. The reason we need strong induction is because in many cases, only knowing PAK is not sufficient to prove PAK plus 1. Therefore, we must include additional information as the premises. In strong induction, since the dependency is multiple, we may also need to discuss multiple cases as the base cases. For example, we may need to show that PA0 is true, PA1 is true, and all the way through PAI is true as the base cases. Correspondingly, in the induction hypothesis, we will assume that PA0 through PAK are true for all k that is larger than or equal to I. Again, we will make the range of k include the base cases. Let's discuss the logic of strong math induction. Again, suppose we have shown that PAK plus 1 is true when PA0 all the way through PAK are all true for k larger than or equal to I. Meanwhile, recall that in the base step, we have shown that PA0 all the way through PAI are all true. Together, we can show that PAI plus 1 is true. Similarly, we can show PAI plus 2 is true, since we know PA0 all the way through PAI plus 1 are all true. Following the logic, we will be able to show that PAK plus 1 is true for an arbitrary index k plus 1. It means that the proposition is true for the entire domain. Again, the reasoning works for both finite and infinite sequences. Let's look at a strong induction example. Prove that for all integers k larger than or equal to 8, k cents can be obtained using only 3-cent and 5-cent coins. We can see that if we can prove that k minus 2 cents can be obtained using 3 and 5-cent coins, we can just add one 3-cent coin to obtain k plus 1 cents. In this case, PAK plus 1 depends on PAK minus 2, PAK minus 1, and PAK. In other words, we need to discuss the first three terms of the domain as base cases. We can make 8 cents using one 3-cent coin and one 5-cent coin. We can make 9 cents using three 3-cent coins. And we can make 10 cents using two 5-cent coins. For the induction hypothesis, we assume that the proposition is true for all values that go from a to k, where k is larger than or equal to 10. Note that since k is larger than or equal to 10, we know k minus 2 is larger than or equal to 8. It makes k minus 2 within the range of our induction hypothesis. Therefore, we can obtain k minus 2 cents with only 3 and 5-cent coins. Now, to obtain k plus 1 cents, we just need to add one 3-cent coin on top of k minus 2 cents. Based on the induction logic, we can claim that the proposition is true for all k that is larger than or equal to 10. Since we have also shown that the proposition is true for k equals 8 and k equals 9 during the base case, we conclude that the proposition is also true for all k that is larger than or equal to 8, the same as the original domain. In summary, we have presented math induction in this video. Math induction is a technique for proving propositions whose domains are sequences. The crux of math induction is to leverage the dependency among the terms of the sequence. That is, knowing the proposition is true on the preceding terms makes the proof of it being true on the current term easier. Depending on how many terms it depends on, we can classify math induction as weak induction and strong induction. Weak induction only depends on the former term, while strong induction depends on all preceding terms. Finally, math induction has three major steps. In the first base step, we show that the proposition is true on the initial terms. Second, we make an induction hypothesis assuming that PA0 all the way through PAK are true. And in the induction step, we show PAK plus 1 is true. Finally, we conclude that the original statement is true. Thank you for watching, and see you next time.